Today we're pleased to welcome Mark Handcock of UCLA's Statistics Department, and the title of his talk is Statistical Modeling of Social Networks.
Actually, I should make sure this is on. Is it on here? Yep, good. Okay. So thank you very much for the invitation to speak to our day. As a faculty member at UCLA, it's a good opportunity to meet with other groups on campus, and as a relatively new faculty member, it's a good opportunity to find out a lot more about what people are working on in the anthropological sciences. Mainly. Okay, what I'd like to do today is give you a perspective of social networks. Is that yours?
It is.
Okay. It's got a very dry voice. To discuss about social networks from the perspective of a statistician, which is a different perspective than in the social sciences, except I think this area has been developed mainly in the social sciences, and the statistical treatment of it's been relatively recent. As a result, I think there's an enormous amount of interplay between the statistical ideas and the social scientific ideas, which has had great positive influences on both sciences. All right, so what I'm going to give today is an overview of this perspective on social networks. Much of the work is joint with people I've worked with: Ian Fellows at UCLA, Dave Hunter at Penn State, Krista Guile, University of Massachusetts in Amherst, and Pavel Kravitsky, currently at Penn State. And much of it is funded by various agencies around. I won't go into a lot of technical details, but there is some of the more technical aspects of it are on my website here, and also on some of the more computational aspects are on the StatNet project website. All right. So basically, I'd just like to set the frame of it, at least from a statistical standpoint. And the core idea of what we're trying to do is model relational information. Now, again, this makes lots of sense from an anthropological standpoint, but it's worthwhile just reflecting for a minute on where the traditional statistical viewpoint has been set. So from there, we have a population of interest. We have units within the population. We have measures on the individual elements of it. And the idea is to look at a summary of those measures, those individual units, treating them as at the atomic level and separately from each other. So the characteristics of the population are the aggregation of the characteristics of the individuals involved. Now, what's different here in the social network setting and in the relational data setting is to look at the relation between the individual units and the population of interest. So the core idea is to look at pairs of units and then look at a measure on those pairs of units, which is a relation only on that pair, or can be thought of intrinsically on that pair, in the sense of it can't be reduced to a property of the individual units involved. Requires two, so a marriage or some sort of social relation of that form. One thing I should mention before I go further on, I'm one of those folks who likes questions as we go along, or you don't have to ask questions, but feel free to ask questions and stop, and I'll be more than happy to delve in some of the side topics, either briefly or defer the answers till the end of the actual talk. All right, so the core idea here is that we'll be dealing with relationships, and rather than looking at properties of individual entities alone, that we could refer to as attributes. And so many examples here with the entities could be persons or other things like that. The forms of relationship could be very varied: communication, friendship, proximity, or so on between them. And so then we can define social network analysis broadly as a study of relational data where the data itself is arising from the study of social systems defined in this way. So fundamentally, social network analysis is about relational information. All right, so just to have some core ideas on the page, most people know, but it's almost, it's important just from a notational, conceptual standpoint, where we define a network here as a collection of entities together with a set of relations in those entities here. So we have here just in these so-called sociograms or graphical representations of them, where we represent their entities by nodes or vertices in this graph, and we have a label on the vertex which isn't required, which gives us an identifier. And in this case, the line between the nodes represents a relationship between nodes, 1 and 2, 1 and 3, but there's no relationship between 1 and 4. And one of the notions of this is, in this case, this relationship is called an undirected relationship because the relationship does not have a direction associated with it, at least graphically. So over here, we see a similar network, except for the fact that the relationship here between nodes is a directional one, where we see the direction of the arrow here pointing from this node to this node. And it's clear the relationship does not need to be reciprocated. It is in this case, but it isn't in some other cases. And we can also have within a network multiple types of relationships. So we have red or purple relationship and a green one also. And we can also have valued or any other functional form on this pair. It could be a count, or it could be some much more complex thing, even a network itself. For example, if each of these nodes here represents countries, we could have the relationship tie between the countries could be a social network of the immigrants to and from either of these countries. So the networks itself can be a very broad notion going on, and I'll be carrying these notions throughout the actual talk. All right. So to come from looking at it from a mathematical perspective, the core idea is the idea of the networks presented on the previous page can be very useful to represent the relationships, just as a nice, simple mathematical representation. And because of this, it's very used throughout many different sciences, both the social sciences, natural sciences, engineering sciences, and so on. This networks being such a natural way to represent relational data. So they've sprung up over the last 100 years or so in that way. And this leads to, from our perspective, a bunch of different issues that's worthwhile keeping in mind. One is that the terminologies used and nomenclature is very different between various sciences involved. Very simple things like nodes or vertices or the nature of these terms changes a lot. So there's very often multiple terms for the same concept, and also very commonly the same concept means, the same term means different things in different fields. So if you're reading the network's literature, depending on whether you're coming from, you'll find that you have to be very conscious of those things to make sure that the terms are very well defined and so on. Be very tolerant to it. And the last one is actually somewhat of a deeper notion here that I think is very important to keep in mind. And the core idea is that if we have, let's say, n objects we're interested in, then we have order n squared relationships amongst those objects. So from a statistical standpoint, we're looking at the interrelationship between an order n squared number of objects that we want to describe. So for networks of any non-trivial size, the amount of structure in that network that you're trying to represent in relational data is very large. So intrinsically, the complexity of the phenomena we're trying to represent is very large. As a result, when we get down to the mathematical representations of it, which are by their nature almost always idealized, we'll find that we'll be missing out a lot in that representation. Going from the real phenomena to the mathematical representation, we'll be leaving a lot behind. So the direct practical implication of that is that network models tend to model some aspects of this complexity well and other aspects extremely poorly. As a result, if you're interested in the aspects which they're not representing very well, the model can look very cartoonish and very, very bad. And if you're looking at it from the perspective of what you care about, it can look very good. So when you're looking at network models in the literature, be very aware of this. Ask yourself all the time, for what scientific objective are they writing down this mathematical representation? And for that scientific objective, how well is the network model representing the components thought to be important to it? And that's really important because we know the network models are going to be missing out an enormous amount. And this last fact also leads to a multitude of frameworks involved. Networks used in so many different ways because the frameworks are, again, very well aligned with the scientific objectives they have in mind. I should just add one other comment that I think this is a very good thing. If you think you can write down representations of complex phenomena that are going to capture everything, that those frameworks are going to be not very tractable from a scientific standpoint and not going to lead to very much progress. So this is a very pragmatic view. All right. I should also mention that understanding social relations to this audience, this is very natural here. Understanding the structure of social relationships has been the central focus of the social science field. One of my favourite readings is Radcliffe Brown's presidential address in 1940, where he gives a very, I would call it a plea, or at least an argument for what's important to the anthropological sciences. But I know in anthropology these debates have been going on for a very long time. But it's really the view that's given here, mainly in the social networks, is very close to that that view. That doesn't exclude other views or concerns about the oversimplification of that view, but it's certainly very consistent with that actually view. So the aspect in social network analysis is then to try to understand how social structures form and evolve, and try to give a somewhat simple representation of it in such a way that the observed social structures emerge as the result of somewhat more elemental social structures. That's a primary conceptual goal of social network analysis or social network modelling. All right. Just a couple of other things here. From a statistical aspect, what we're trying to do is represent social relations via networks. And this last one here is actually quite important to the statisticians. I could have a lot of discussion of this from a philosophical standpoint, is that we're looking at what we observe as a realization of a stochastic process. That is, what we see is data which is produced by some overall latent social forces, and our ultimate goal is to describe those latent social forces. And this leads us to place most of the data we see within this stochastic frame, that what we see is a realization of that stochastic frame, and that's quite important. All right, and I'll also focus on data of at least 3 different forms. Even though the conceptual focus is much on the relational data form, we do note that for almost any realistic modelling, individual level information is vitally important to the process, not only guiding individual behaviour but also guiding social structure. That must be taken into account. Relational data is very clearly the focus. Also population level data as well. That is, we might not have data on individual dyads or individuals, but might have data on the network as a whole, information on the network as a whole that needs to be taken into account. These are some somewhat narrow statistical case. I should also obviously measure, historical contingency. Placing the networks in a dynamic or temporal framework is vitally important as well. And I just don't mention it here, and I could make lots of comments on that if there are questions at the end about that aspect of it. Okay, I'll just also say that the theoretical representations can be decomposed in a different form. This is saying about where the data is coming from, but the actual social forces that lead to network structure can be represented in the same way. No questions so far? Okay. All right, the other thing I just briefly like to do is to look again at where the literatures for social networks have been developed from. Because again, they've developed somewhat separately until recent times, probably the last decade or so. Now, our social network community going back 50 or 60 years, and there's some, I just put in some references here, not the important ones, but, oops, I've got a typo there, that should be 1940. But these are some various important folks, Overfrank, Heider, Holland Leinhardt, folks like that. They've been working on the conceptual sides of this for a very long period of time. The statistical networks community is relatively new. It's really only, well, depends how you measure it, but I would bring it back to, say, the mid-70s, early 80s. That's still quite small, but has had rapid growth in the last decade or so. There's people working in the statistical sciences. A lot of the ideas have come out of the spatial statistics community, and I just mentioned Julian Bisag's seminal work. And the core idea is in the spatial statistics, we're trying to measure latent structures which have an underlying spatial component to them, can well be defined by the spatial component, but they're also unknown dependent structures. And from a mathematical standpoint, this is closely related to social networks where the dependent structures are also latent and unknown. So lots of the ideas for the social network models actually came from spatial ideas. And I should also mention that the source of these was this statistical physics ideas coming out of the 1950s and 40s also. So there's a common core to all of this work, but they've developed as sort of branches of a tree, if you will, in the specific areas. From a statistical perspective, the statistical exponential family theory has been very important in this field. And I go back again to the seminal work of Barndorf-Nielsen. It's very important because this work enables us to represent complex multivariate distributions through relatively simple and tractable ways. I should also mention, for those of you who are thinking, the graphical modelling community, which has been very big since the 1980s, would seem to be directly relevant here. And as it turns out, it's surprisingly orthogonal to a lot of the work in the social networks. And the reason is here, to a large degree, this graphical modelling community has been interested in cases where the nodes themselves represent random variables and the ties represent various forms of conditional independence relationships amongst those. So it's very different from the case that I'm in, and the social network community is mainly interested in, where the nodes are real individuals or real phenomena, and what we have is multiple measurements or direct measurements on them. Although it does turn out the structure of the statistical models can be very well described by a lot of the graphical models, but that's a separate issue. In the last, certainly 10 years, the machine learning community, computer science, has led to enormous amount of work in social networks, especially latent models and Bayesian representations. I could say a lot about that, but that's led to very rapid growth. And if you're working in this area or thinking about modelling in this area, taking into account what they've been doing is very important, and so on. And probably since the turn of the century, physics and applied math, looking for to apply their ideas in the natural sciences, other sciences, has been working in this area. I could say a lot about that also, but this work has certainly made a big splash. Okay, and a lot of work in probably the last 5 years in ecological networks, food webs and other forms like that. But my main focus is going to be on this sort of standard social network core ideas in social networks, so in this theory going back a somewhat length of time. All right, so to fix ideas a bit, I'll talk about a sort of somewhat stylized but still interesting example. It's a classic data set collected by Sampson during his PhD thesis in the late 60s. And what he did was go to a cloister and observe it over a 12-month period of time, looking at trying to understand the social structure of a small monastery. And while he was there, there was and this was the 60s, the late 60s, there was a very rapid change in the social structure of the monastery, in which he was able to observe through the entire process. And this led to a large amount of data on the social structure, qualitative analysis, and Sampson's thesis was basically a qualitative analysis of what he observed. But he also did a lot of direct measurements through the 12-month period, and here's some of the data from it. So what we have here are the nodes being the 18 monks in the cloister, being the red dots, and the lines here represent a particular measure expressed of liking. So what he did was sit down with the 18 monks and say, tell me the other monks which you like in the cloister. So this arrow says this monk nominated this monk here as someone he actually liked. And there you have it. You can see the tie. So this guy liked this guy didn't like that person back, but we've got a mutual effect here. So this is a standard sociogram or representation. So just to be explicit, in terms of observation, he then went to ask each of these individuals involved, all 18, gave them the survey with a list of all the other 18, took the nominations and constructed this graph. Okay, so this would be a simple example of what we're doing. And it is interesting to note, and I would make one interesting comment here, is that note the information we have is basically binary information for what's actually going on. And I haven't described to you at all how I place these dots on the actual page. And more importantly, the placement of the dots, although we'd like it to reflect the social information given here, also reflects the fact that we're displaying it in a two-dimensional page, and the actual geographic location is an artifact of whatever layout algorithm I've used. And this, for a social structure, is a very important thing because there's more here than what the data actually says. And we could say a lot about that. I will say a lot if prompted, so please don't ask.
To what extent, well, how big a structure can you analyze without getting into big trouble?
That's a very interesting question, and it actually comes back to the comment I made earlier about complexity. So if the short answer, sort of glib answer, is that if the complexity of the network's very low, it's unbounded. You know, I could easily analyze a 300 million node network and get very simple descriptors of it, build perfectly reasonable stochastic models for it if the structure is very simple. Now, if you have a network like this, even with 18 nodes, if you have 18 nodes, we have 18 choose 2, you have 200 odd dyads involved, and then for those 200 dyads, if you think about that as a multivariate random vector, we're then looking at the structure of a 200-dimensional random vector. So even with 18 nodes, if that structure is complex, suddenly I can't even analyze 18. So it does, and this is sort of the more scientifically relevant answer, it depends a lot upon A, the structure that you're looking at, and B, the particular objectives in mind. For my 300 million nodes, if I say, well, all I'm really interested in is the relative propensity to form ties, I can analyze 300 with a relatively simple model. But if I ask myself, what are the underlying social forces that lead to the migration patterns we've seen in the United States over the last 50 years, then suddenly I'm completely out of luck. I do think there's a middle ground involved, but it depends a lot on the particular question involved. And I think this is the correct answer to it because the answer that given a certain network size or shape really misses the fact that it depends enormously on the scientific question. Okay, so here's an example here going in it. Sampson identified three groups, well actually four. The so-called young Turks, the loyal opposition, the outcasts, and what he referred to as the waverers. And so I've identified those with a list of characters, the outcast over here. And what's interesting going back to look at this pattern here, so I didn't do any clustering on this, we just saw them lay out on the page. And here's the same layout with his groups. Now he did this from 12 months qualitative analysis, and these are the labels when you do it with this layout algorithm. So the colours probably exaggerate it, but we do tend to see clusters in this way. The Young Turks over here, a little bit on their own. The loyal opposition, perhaps a little more spread out over here. And the outcast being well outcast. So we see this component over there. Now, I could say a lot about what it would mean to define clusters. They could, in this case, we're using the fact that we've got a spatial layout and we're clustering them spatially and correlating that with a social structure. But we need to be clear upon what clusters actually mean. At its core notion, it seems to mean more within cluster ties than between cluster ties when you account for other things. But the concept of clustering is very dependent upon the actual definition of it. Okay, so it would be interesting to look at these things involved. So looking at these very simple examples, I think is helpful because it gives us a sense of what's important or not. So here's one other one on a slightly larger scale. It's a national longitudinal study of adolescent health, which many of you might have seen. What it is a school-based study of adolescents, nationally representative one in grades 7 through 12. And what they do is go into a bunch of high schools, 162 in the early 90s, and asked individuals, amongst other things, to nominate up to the 5 best boy and 5 best girl as friends. And so they had this list there. And here's an example of one of the smallest schools there with a layout. So each of the nodes represents a student. The label represents the grade they're in, 12, 11, and so on. And then we have the actual friendship ties. Here's a grade 7 nominating a 10 and so on within this pattern. And we have a different layout here as well. So this is a very small school, but you can see we have the different grades involved. And again, one of the things we notice is a clustering. The 7s appear to be over here, 8s. The 9s, interestingly enough, appear to be split between a group of 9s here and a group of 9 on the side. And the 10s and 11s and 12s, although you see patterns in them, appear to be laid out in this way. So we can observe things by looking at these components, which I think is extremely interesting. All right, question?
Sorry. So when you're showing these, is the structure produced by some sort of an algorithm to minimize the distance of all the appropriate relations, or how do you produce something like that?
That's a very good question, and I've sort of been cheating a little by not answering it, but I'll answer it now as a teaser and then come back. What I've actually done is fit a relatively sophisticated spatial latent space model, a stochastic model for the entire network that postulates that the social structure within this network can be represented in an underlying geographic space of 2 dimensions, a 2-dimensional Euclidean space. And these are the most likely spatial positions of these nodes consistent with that social structure. There's a lot of methods that go along with that, but that's a core conceptual notion. So interestingly enough, this does not use a classic layout algorithm used in graphics layout, which uses minimum stress criteria. It looks at the most likely points within the context of a theory, a social theory, expressed directly through a stochastic model. So that's my cheat. I've actually laid out the spatial scale here to do that process. And I'll mention these models right towards the end. Okay. So here's a somewhat larger one just to go through. Here's a school with 2,200 students, and we actually see that attributes matter a lot in this case. We've got the grade here. You can see the clustering based on grade, based on the colour. And we do the same thing based on race, and you can see that this has a large number of Hispanics. The whites are unfortunately in the background, but they're over here, and blacks and so on going on. But you see a lot of potential clustering based on the race variable, including the grade variable. So it's clear that attributes of the individuals are going to matter in addition to other things.
So, Mark,
Yep.
so are the people who have no ties, are those people, is that missing data, or are those people who actually said they had no friends?
Right. Within this, the short answer is there's no missing data involved. So as a result, we know them to have no friends. And I've just sort of cheated by just laying them outside the edge here to put them on the actual graph component. The sort of more true answer is there's actually substantial missing data in this. I could describe them in the ad health data. There were some students who didn't go to school on that day, so we don't have any of their out ties. Some people nominated people who weren't in the universe of interest and so on. So there's actually a very complex structure of missingness which I'm not addressing here. I could say a little more about it. Okay, but these are definitely isolates in the jargon of network analysis. So now just to go through those examples, it brings together all these different features we think might be important to represent within social structure. One being the mutuality of ties. For directed ties, if I send a tie to you, is it more likely for you to send a tie back? It's a fairly fundamental thing. Other thing that is very important is individual propensity to form ties, and that's going to vary greatly across individuals. Some people just don't form ties very much, don't nominate many friends. Other people are going to have many friends and be hubs or sinks or other forms like that. And so this heterogeneity, people are dramatically different in this, needs to be taken into account. Another thing which is vitally important and focused along a lot by the sociologists is the idea of homophily by actor attributes. And this is nothing more than a high propensity to form ties between actors with similar attributes. If you have people who are friendship relationships, if they're co-located in space, they're much more likely to form ties than if they're on the other side of the country or not. All of these other attributes involved. And just mention some of them here. Now, this doesn't say that this is an, if you will, a correlation-based idea. It's not saying that these attributes are in some sense causing the relationship, but they just say they're closely associated with it. Couple of comments here. One is attributes might be observed or unobserved. So there might be an underlying unobserved attribute which we have homophily on, which we don't actually see. So this turns out to be very important. Note that this is within dyad idea. This is an individual level idea. Individuals vary in this. This is a dyadic level because you look at the attributes of the both individuals involved. Now, transitivity of relationships, this is a classic friends of friends have a high propensity to be friends, which we see an enormous amount. And this is a triadic level. You need 3 individuals to have this form going on. And so we're moving up as we move from very simple configurations to more complex configurations. And the next one, it's also transitive, but getting a little more subtle, if you will, is the idea of balance of relationships. And this is a psychological idea going back to Haider, and it's very, there's a lot of nuance involved in it, but one of the simple ways to feel about concept is people feel comfortable if they agree with others whom they like. So the idea if you're having positive affect relationship, that the ideas looking at within triads of individuals, you'll get balance of opinions within those 3 individuals involved, and the friendship relationships will try to be consistent with those. And one of the key results of this theory is that over time you'll see the individual triads involved in a social network will evolve more towards balance of relationship within those triads. So this underlying theory can be represented mathematically and then stochastically and incorporated into many of the models. And the last thing here is there's been some arguments of the social theorists to make triads, not the dyad, the fundamental unit. It seems natural the way we're describing it to have a dyadic level representation. But similar here, and others were arguing that the triad is the least that we should be looking at in terms of the fundamental unit. To keep in mind within any dyad that social relationship only makes sense in the context of having an observer or a third group outside observing that relationship, and social should be based on 2 rather than 3. But there's a lot of other features moving through these that we'd like our models to represent accurately. Just a couple of other comments here. The choice of models depends upon the objectives I've made earlier. The primary interest in social network analysis is the nature of the relationships themselves, and this is true and through of a lot of the social sciences. How the behaviour of individuals depends upon their location in the network, depending on how location is defined and conceptualised. How the qualities of the actors, attributes of the actors influence the structure of the network. Clearly very important things. These are sort of the 2 primary scientific viewpoints. But where these go, how secondaries on how a network structure influence processes that develop over it. So what I do and a bunch of other people do is have a stochastic model for the network and then have a stochastic model for some process of transmission that comes over it. One of the things I've worked on a lot and other people have is looking at HIV spread over sexual networks with a core idea of how the network structure influences a stochastic process of HIV spread. And the last one, and this is where also vitally important, is the effect of interventions. One of the core motivations for developing network models is to come up with, in essence, a virtual laboratory to represent idealized social systems through the stochastic and mathematical representations. And then what you would do is make a change to that social system because it's virtual, it's under your control, and then look at how the change to the social system influences the spread of disease and the nature of the relationships itself. So basically, looking at the influence of interventions is very important. And of course, in the HIV case, through changing either the social structure or the transmission process, how to inhibit the spread of HIV has been a very important, if singular, goal. All right. Okay, and the last thing, and this is again just a point to keep in mind. I've made this before. I want to make it somewhat explicitly. Is that a couple of perspectives. A lot of social network analysis has a sort of network-specific perspective, by which I mean the objective scientifically is to describe the structure of a given network. We have a complex network, a lot of data. We want to just come up with numerical summaries or numerical descriptors to describe the structure. What the centrality of that network, we want other forms of it. Now, as distinct from that is the so-called population process approach, where the actual network we observe is the realization of these social forces, and we don't care about that network very much, except to the degree it helps us understand the social forces that generated it. So the difference basically is there's a primary scientific objective, the social forces that generated what we see, or a description of what we actually see. And it can vary depending upon the cases, although most of the things I've talked about really deal with this population process approach. Okay. Now I'll actually get into the statistical models for social networks, some of the specifics just as an overview, two different forms. Before I go on, there are any just brief questions about the sort of introduction material, the material so far? Okay. So let me describe a social network consisting of n social actors. We'll define them and we'll have a relationship on them and variables on that set. So I'll just define Yij to be an indicator of that. So if there's one, if actor I, there's a relationship from actor I to actor J. It could be directed or not. I won't make too much of a difference in this overview. And then we can think about pulling these variables together into this matrix, so-called matrix Y, which is an n by n socio matrix. And we can think of it as an n by n by one binary array of these variables Y. So there's the order n squared right there in the form. We'll also have a matrix of actor level covariates, X covariates on these, and will be Q. We'll just write them in this way. And so the basic problem is to write down a joint model for the outcome of the relations conceptualized as random variables and the actual actor attributes represented through X here. So clearly there'll be a multivariate structure in here, a multivariate structure within the X's, and also, most importantly, an interaction between these two. We'll need to represent all three of those well. All right. So I'll describe now a general class of these, and these are the exponential family random graph models, and they've been used a lot, and they're of great interest. So I'll just give a conceptual view of them. There's some technical detail on this slide, but I'll make it clear what's actually the core idea. The core idea is to represent here the conditional relationship of Y of the relations given the attributes here, parameterize it in the following form, where it's e to the eta multiplied by some set of network statistics G of, depend upon the data, conditional upon X. So the core idea is we represent the entire multivariate structure of Y given X, i.e. the relations given the attributes, by this exponent of this linear function here. So what the G is some form of network statistics, and by which we mean some mathematical function of the relational information, but might also depend upon the attributes, and typically does. Now we note within this exponential family, the statistics here are jointly sufficient for the model. So we're in essence saying that all of the stochastic structure of the interactions can be explained purely as functions of these statistics. So we're dramatically reducing the complexity of this down to this form. And this guy here is just a normalizing constant kept in there so that the sum of this sums up to 1. So it's explicit representations here. Sum over all possible graphs of the numerator. Now the other thing to note is because we can choose G within this model, the set of network statistics, we can make this arbitrarily complex by choosing a large number of vector G, and also the complexity of G can be very complex. So we're not actually, this is more a representation because any multivariate distribution can be represented in this way, but the hope is to have a very parsimonious representation, to have a small number of features in it. And these, as many of you will know, is a statistical exponential family, and because of this, a lot of the statistical properties of these are reasonably well studied. And there's an argument that the exponential families are either broader class of, if you will, nice statistical distributions we can deal with, and so it's both broad but also somewhat tractable. So I'll give some simple examples of models within this class because they're sort of useful. The general form seems a little abstract. So suppose the yj independent and equally likely, i.e. for each possible relationship, it's in essence a coin toss with probability p that there's a relationship there or not, and the relationships are all independent of each other. Well, then we can write the log odds of a tie between an individual as just eta, the logit of the marginal probability that I equals j, because of independence, there's no loss there. So then we can just write down with one line of algebra to show that the probability distribution of y doesn't depend upon covariates here, but it's just e to the eta times this statistic here, which is just a sum over y, i.e. the sum of the possible ties, and the number of ties involved. So we can then reduce this network model down to just one univariate statistic, which is just a total number of ties. So it's extremely simple. And this is the Erdos-Renier model, which has been enormously studied in graph theory and mathematics, is a simple case here. But although it's good for mathematical analysis, it's not so good for real phenomena because we're assuming relationships are independent and also equally likely. Now we can make that more general relatively straightforwardly by saying the y's are still independent, but they depend upon some dyadic covariates x. We could have a q of those. If you remember, there were the q of them. So we can actually write now the same thing where we have the statistics g are just cross products of the y's. So in essence, these are just, the statistics are just averages of the dyadic outcomes where they're in essence counts of the number of times or counts of the x's for those which relations occur. And if you look at this a little while, so this gives us a nice complex model because by the choice of the x's, which we have complete control over, it gives us a very flexible class of models. But again, if you play with that a couple of lines of algebra, you notice that the logit, because of independence, the logit of the probability is just equal to a linear function of the covariates here, where these are just the eta k's, are just the linear values involved. So in actual fact, this is just logistic regression. When you add to this functional form the independence assumption, it's in essence saying that we can just do a linear regression on the relational variables, and this is what the model actually says. So even though this model is quite flexible up to independence, it's effectively logistic regression on the network on the dyadic level variables. So clearly what we want is able to put in more dependent terms here. So I'll just describe those briefly because they're sort of the more sort of advanced or innovative aspect of it. There's a seminal paper by Overfrank and David Strauss at UC Davis in the 80s on what they call Markov random graph models, which are an example of this class. And they wanted simple models that represented dependency. And so what they did is say that the yij in the graph, the relational variables in the graph that don't share an actor, i.e. if you think about a relationship is incident upon two different nodes, then if you have two different relationships, if the nodes aren't the same, either the bottom one or the top one aren't the same, so they're not incident on the same person, then we'll say that those relational variables are conditionally independent given everything else in the graph. So it's basically saying the dependence comes about because you have the dyad incident on the same node. Then they did an analysis of this, and they showed that the only important things, you could then reduce these models down to models just in terms of the so-called degree distribution, which is accounts of the proportion of actors of each degree, and by degree I just mean number of ties. So it's basically a model for the overall propensities to form ties and the number of triangles involved. And by triangles, they just mean complete subgraphs of size 3, i.e. the counts of the number of times you'd have 3 different nodes and you'd have all of the ties existing in the actual node. So they showed with this simple idea of nearest neighbour based on the nodal identities, you could actually reduce it down. All of these models could be expressed in terms of the individual propensity to form ties and transitive effects. So this meant you could have these very complex forms could potentially be described in these relatively simple statistics. So this was regarded at the time as a very big step forward because, again, you would see emergent social structures coming out of relatively simple forms. As it turned out, it was a disaster practically, but it's not clear from looking at this that that's actually true. I believe it strongly. It would be very difficult to look at this and say that it's not going to work. And the reason it didn't work was that the sort of structures that came out of this tended to be too constrained. There were some attempts after to make these more general mechanisms involved, and the core idea here is just to come up with ideas of broader neighbourhoods and just a closest neighbour based on the number of nodes. And so what we do here is look at, our idea is to look at, say, this relationship here and this relationship here, and if those two relationships, if they were in place, don't form a cycle, that is, a set of steps you could work through in the network, a complete pathway throughout the actual nodes, then you'd in fact have independence here, or conditional independence. So this was developed by Tom Snyder, Pip Patterson, and Gary Robbins. So these guys, it's a second order neighbourhood which greatly increased the class of models you could actually have and the class of statistics involved. And this led to sort of more interesting statistics, these so-called edgewise shared partners, the degrees of counts in which you could have multiple partners, or another way to think about it, multiple pathways to get from I to J, instead of just having a single path, which is a triangle having multiple paths over different alters, and so-called dyad shared partner forms, which I won't go into these forms. Just in terms of timing, should I finish at about 1? Is that good, or okay?
Well, you have to 1:30.
I have to 1:30? Okay.
Any way you wish.
Well, I might finish then about 1:15 if that'll work, if that's good. Okay, just in terms of going through. So they led to statistics of this type. Now the last thing is, well, what happens if we wanted to move out of these two classes, which are based on symmetry ideas? Then a lot of people have worked on this sort of structural signature notion, and it was sort of to go to a different, rather than going to this sort of mathematical theory, to say, well, why didn't we come up with characteristics in the network which just seem intuitively of interest, or just based on some substantive theory? So here's an example of one. Clustering is pretty important. So we could start with, say, the number of triangles in the graph, and this is just a way to mathematically represent it, but it's because they're binary variables, but just to count the number of triangles in it. And we can think about a modification of that, where we could take the number of triangles here, count them, it's a statistic, and divide by the number of 2 stars, where 2 stars are described by a configuration, a triad. We have an ego node, and we have a ties from the ego node to 2 of the alter nodes. So you can see what's called a 2 star. You get to 3 and 4 star. You can see it has like a center ego and all those star links coming out. Well, this is a simple version where you have just a single link coming out. So if you think about the comparison between these two things here, the difference between them is the presence of the tie between J1 and J2 in this case. So you're basically saying that this is a sort of a proto triangle, if you will, that may or may not have a tie between here. And this is when the tie actually exists, the completion of that. So this is, in essence, the number of actual triangles in the graph divided by the number of potential triangles, or near triangles, if you will. So it gives an idea of triangle density within a state of near triangles. The 3 there is just because of the symmetries of where the ego node goes. So the idea here is this gives you a ratio between 0 and 1, which gives us a ratio of the density of the transitives. So this seems like a pretty useful statistic involved. And it doesn't come out of the previous versions I looked at, the Markov forms, but still seems to be useful. So we could just use this as a statistic in the model involved. And this is referred to as the mean clustering coefficient in the applied maths literature. And it's been used a lot as a measure of local clustering or transitivity. But note that it doesn't have a nice, simple, symmetry-based interpretation of it. Now, I could say a lot about inference for them. Now, since we're writing down the full model, I'll just go through this. So they're involved in, I could give many lectures on these topics. How to do inference? Well, if you've got data on a network, how do you infer the characteristics eta? Well, there are many ways to do it, but the most natural way is to use likelihood theory. You've got a full probability distribution, so convert that to the likelihood of observing what we actually see as a function of the parameters of interest. And then you could either compute that likelihood here, and this is the log likelihood, which is easy to express in terms of the observed graph, and do the sum over here to compute the likelihood. And then you could do maximum likelihood, or you could do Bayesian-based inference on that. Now this is actually hard because the sum of all possible graphs. So there was a cottage industry in the last decade, which I was involved with, and as many other people, on how to approximate this likelihood. And we did it via Markov chain Monte Carlo methods and other things like that. And other people worked on this as well using classic MCMC ideas. So I won't say so much more about that. Although we used some very good work by Charlie Guy and Elizabeth Thompson to approximate the MLE. And by the way, this approach gives us a way to generate graphs based on a given probability model, which is very useful in the virtual lab side of things going on. I'll just give some illustrations of the sort of things that will come out of it. So here's a case where you have, say, 50 nodes in a village level, and we want a mean clustering coefficient, the thing I just described, of 15%. And what's often referred to as this is a degree distribution following a Yule distribution, which is, for those of you in the know, this is a so-called scale-free or power law distribution with a scaling exponent of 3, i.e. a very right-skewed distribution. So 15% of the possible values were actually, of possible triangles were actually there, and we can scale that up to 1,000. But let's look at the 15s first. So here's a 15. Now the difference between these guys here is that this one is the one with 15% clustering. You can see the clustering of the ties over here, and you can see the right skewed degree distribution as well. Now over here, ironically, this has exactly the same degree distribution, but has 0 clustering involved. And again, you can see the impact of visualization. Now, of course, because we have clustering in the model, we can directly control it through this form, so we can just have a direct representation of both these forms. Now, here's exactly the same model, but based on 1,000 nodes. And this doesn't have any clustering involved. And you can see here the clustering, you can see threads of ties running through it. To get the clustering at 15%, it needs to run these threads of relationships to get these closed triangles involved. This also points out how, when you're looking at visualizations over small network sizes, it's easy to do, but with 1,000 you're suddenly running into problems because you don't see a lot, because it just seems like a big splat ball on the page. And it's sort of jokey to say that in a way, but it also says why statistical models are so useful, because visualization is very useful and it's good to use it as much as you can, but if the networks are sufficiently complex, it becomes very hard. And as a result, coming up with numerical and other ways of representing structure is much more important. And we can do the same thing if we add attributes involved. Say this is a heterosexual network where we have 2 different types and we have relationships based on that, where almost all the ties are heterosexual. Over here we do the same thing with a strong correlation involved, so we get the different clusterings involved. And we can do the same thing here with a positive correlation or even a negative correlation in this form. So we can do lots of things along these lines. Yep.
So with the correlation coefficient that you have that's based on triangles,
yep,
you could still have a very interconnected network like the one you showed on your last slide. with lots of threads, as you call them, right on the right, that are triangular, right? So you have four-sided, five-sided loops or rings or whatever.
Yep.
So you need some. Is there a general cluster? Is there some clustering coefficient that looks at distributions of different
Yep.
given triangles, like all the more complicated ones?
That's
together?
exactly right.
Yeah.
Yep. That's exactly right. You can look at various forms of clustering going on. For example, although I didn't emphasize it very much, the so-called shared partner distributions do exactly that. I'll quickly flip back because of this comment here. We look at the shared partner counts, which they're basically giving you these triangle clusterings involved. They give you the structures involved because you have 1, 2, 3, 4, 5, 6 nodes. So we look at the distributions of these over different Ks, and that gets you exactly this form of local clustering involved. And that's one thing. The other just comment I wanted to make on this is that note that all of the structure we see here is emergent from this very simple, almost cartoonish type model with only 2 different terms in it, that we see all the structure. So the higher order structures of clustering, 4 and 5 nodes, are purely emergent, purely the results of this lower order form. So that's both good and bad. It's good in the sense of you still see higher order structures with very simple representations, but it probably also says we're going to be missing a lot because there are going to be forces working at these higher levels which aren't being captured. Okay, so I have an example here of doing inference with the protein interaction network for fun, and here it is here, but I won't actually go through it. I'll just say that using this approach and using these computational tools, you can get estimates of the parameters involved, and you can get standard errors for them and the standard inference we get from linear models or generalized linear models. It looks very similar to it because of the structural form, but I won't emphasize that here. I'll just have a couple of other, in my few minutes here, I want to talk about 2 just general other aspects that might be of interest. One is when you have partial observation of the social networks, and this has 2 ramifications. And it's, in essence, you have partial observation because you either didn't observe elements, like if you missed elements in ad health studies I mentioned earlier, or you have a very large network that's hard to find or hard to reach. The nodes are hard to reach. And you use a sampling method to observe that, but you don't observe all of it. You only observe a component of it. So just to give a couple of ideas on this, the reason I wanted to discuss these is because they're of interest in their own right, and also because methods have now been developed where you can do inference from them. You don't have to presume you've observed everything to do inference. So we won't go into the inferential procedures only because a lot of technical detail, but there's a lot of hope here. So the sort of things firstly are called sampling designs, and I have a sort of a simple illustration here. So here's a simple network within a firm, and so we just ask 10% of the employees about who they collaborate with. Well, that means we randomly sample 2 of these folks and ask them about their outward ties, who they nominate as collaborators. So all we observe are the ties going out from these individuals, and all of these other ties we don't actually see. This is a classic egocentric design. And so this is often done, and very commonly done. Most network data is of this form. You randomly sample individuals, you ask them about their egocentric networks. But there are other things you can use in studies which I think are of great interest, so-called adaptive designs. And the idea is you start in the same way. You egocentrically sample individuals, and you ask them about their out ties. But then you go out over these out ties. So you start out here, and this person nominates this person here. Then you identify this person from information given here. You then go out and you interview that person and repeat the process. You then ask them about their out ties. And so for this person, you get out in this way to this person here and this person here. So you pick up additional people in the actual node. So note, it's adaptive in the sense of you're using information you collect through the actual process to find out who to sample next. So you might not necessarily know who the individuals are before you actually start the sampling process. And then you could repeat that process, so-called snowball out through it until you pick up more and more people involved until in the end you got everybody. So the advantage of the adaptive sampling is it tends to work better in cases where you don't have a sampling frame of all the individuals involved, A, or B, you use the social capital of the individuals involved to improve the chances of response by other individuals because they're recruited by people they know and have a social capital contact with. That's a very important point, and so on. And the last thing is the actual amount of information you gain from an adaptive sample can be more than the amount of information you gain from a simple random sample about certain attributes. So though the sampling designs need to be tuned, they're enormously advantageous. So other things we could have for partial observation would just be missing data, where I gave a question on ad health. Yep, go on.
Interrupt, but I want to
Yep.
ask about the adaptive samples, which are respondent-driven sampling design.
There or other forms.
Yeah, or
Yep.
other forms.
Yep.
That's one example.
Yep.
So are the statistics now developed to be able to decide whether you've got how much bias you've got in the sample, or what kind of inference you can make from those kinds of samples? I think when you and I
Yep.
talked a couple of years ago, that you were working on it.
Yep.
So what's the state of the play now?
Well, it's the simple answer is yes and no, because the more sort of nuanced answer is yes under mathematical and stochastic assumptions about the sampling and the structure of the network. So if those assumptions are true, you can do inference from it, but there's still quite strong assumptions involved. And yes, a lot of people have worked on it in the last few years and made a lot of progress on the problem. But there still is a real concern, for a pragmatic concern with those designs, about the strengths of assumptions necessary to make valid inference from it. But I've definitely worked on those, and I think there's a lot of hope for improvement. But there'll always be this tension between the strength of the assumptions and the results you actually get. But I could, I'd love to talk about that in an entire lecture about the things involved. But the approach is basically we've taken, essentially write down a model for the underlying network structure and then do inference within the context of that model. So the so-called model-based approaches, where most of the approaches until recently have been so-called design-based, where they're just purely based on assumptions about the sampling design, which tend to be much more sensitive to deviations from those assumptions. If you use a model-based approach, you can use the model to correct for different biases. I'd love to talk about that more, but I won't. Yeah. Okay. And so missing data, I think, which is quite natural, where you just don't observe ties because of this form. And the last one, quite important for anthropological applications, is the boundary specification problem. In the basic idea for here, if you had, say, contractors on the outside and they were collaborating with people on the inside, then they clearly change the social structure, but they're clearly not part of the core organisation either. So how do you take into account who's in the network and who's out, and how do you take into account social influences outside of a network which is of primary scientific interest? And that's less a statistics problem than initially a conceptual problem, but it's worthwhile taking into account. It is quite important for a lot of these studies. All right. So I have an example here of doing inference for it, but I also have another example of these so-called latent space models, which I'll just briefly say, which to do with the layout, and then I'll call a gap there, and we'll, these are here just for, because I like to, I'm sorry, it's not easy to skip ahead to these. Here we go, finally. So the latent space models we were talking about, and there's some notation here, but the core idea is we posit the existence of an underlying space. It's a hierarchical model for the network, where within the social space, the distance that people are apart in the social space determines their propensity to form ties. So the blue equation sort of lays it out, that the log odds of a tie is a function of the locations of the positions in this social space, function of covariates, but also a decreasing function of this distance. The core idea of this distance is unknown, it's latent, and we have to build a model for that distance. So there's a lot of work done on that, a lot of very good ideas by Peter Hoff and others working on these, and our latent class model, which I won't describe, by Nowicki and Snyders. So I won't, and this model can be generalized in certain ways, and we've used it to look at clusterings, and here's the actual clusterings of those for the monks data I looked at before. One of the advantages of it is it can measure the propensity of individuals to be in given clusters. So you don't have to say they're in the cluster or not. There's some uncertainty involved. And so these young Turks here, there was some chance that some of these young Turks were outliers. This is actually a pie chart with the split of cluster membership allied over the actual monks. So I won't describe this anymore. I'll stop here. Well, I've got just one other thing I'll end with is the ad health example which I showed. Here are the estimated clusters for the ad health, and they correlate reasonably closely with the actual grades, the 7s, 8s, except it split the 9s into two groups. It identified there were splits in the 9s, and it merged the 10s and it merged the 11s and 12s in together into one social group. Question?
Yeah, if you use a three-dimensional plot instead of a two-dimensional, will it make much of a difference?
It's an extremely good question. As it turns out, for neither of these do you need the extra 3 dimensions involved. But it is a good statistical question, is if you increase the dimensionality of the latent space, you have more space, if you will, to place the points out. So intuitively, you'd get a better fit involved. It's just a trade-off about whether the additional complexity of, in essence, adding n more parameters to the model is important enough for it. So that's certainly something you need to look into for any application, what the dimensionality of the space is. For both of these, it looks like two dimensions works well, but it does really depend upon the application.